Hello grade 12s, welcome back to another video. So in today's video we'll be starting and kickstarting term 2 physical sciences, and the first topic that I will be doing with is Doppler effect. So for term 2 you have to do work, energy and power, Doppler effect, rate and extent of reaction, chemical equilibrium, and acids and bases. So on today's video, we'll start with Doppler effect. That is the first topic that we'll be doing. So it's a very short topic, so I'll just do it today and finish it with you guys. And if you're struggling with mathematics, business studies, physical sciences, and economics, I have a WhatsApp class whereby you pay 300 Rand per month and 50 Rand registration, and you'll be getting question papers, exclusive videos, and notes, and you'll be able to ask questions whenever you do not understand anything. So if you would like support through your matric year and you don't know where to get it, the Intuitus is here for you. Share it with your friends and families. We are here to help you guys kickstart your matric year with a bang. Okay, we still have time. Maybe you didn't perform well in term 1, but that can still change. So with Doppler effect, you should know waves, sounds, and light. It's a prerequisite. So you did them in grade 10. You need to revise on that. It's very important that you know them. And with regards to the ATP, is that you have to know to state the Doppler effect and explain using illustration the change in pitch observed when a source moves away or towards a stationary listener. And then you have to state applications of the Doppler effect. You need to know ultrasounds, waves in machines, and so forth. And you have to know how to solve problems using their formula. I will show you. And then you need to know wave, sound, light, or you need to know waves, sound, and light in Doppler effect, which is grade 10 work. So it's very, very, very important that that's what you know. So let's take a look at this. We did waves, sounds, and lights in grade 10, and then we are now taking it further in grade 12. So in grade 10, you did frequency, wavelength, period, amplitude, wave speed, and pitch. In grade 12, we'll be doing Doppler effect equation, application of Doppler effect, and Doppler effect with light. So that's what we'll be doing in grade 12. While in grade 10, you did this. If you have a grade 10 cousin or friend, just go and ask for their notes in order for you to revise, or you can watch grade 10 waves, sounds, and light videos here on YouTube. So with regards to waves, sounds, and light from grade 10, we did frequency, which is the number of wave pulse per second, and the SI units for frequency, it's hertz. And then we have period, it's the time taken for one complete wave pulse, and the units for period is seconds. So period is time, and we have amplitude is the maximum displacement of a particular of particles in its equilibrium position. And then the SI units for amplitude, it's meters. Anything with meters is amplitude. And then we have wavelength is the distance between two successive points in phase. And then the SI unit for waves is meters as well. And then we have wave speed is the distance traveled by a point on a wave per unit time. And the SI unit for speed is meters per second as well. So also here is the examination guideline, objectives for grade 10, and here is everything that you need to know: the crust, the amplitude, the period, if you had forgotten about that. And here we'll just look at a few calculations. That frequency, when referring to sound waves, frequency can be referred to as pitch with regards to sound waves. Okay, for example, a sound wave with a higher pitch means the sound wave has a higher frequency. So when the pitch is higher, the frequency is high as well. And then the formula for frequency is the total number of waves divided by total time, or we can say frequency is 1 over time. Okay, if you know the total number of waves, you can just write the total number of waves, and then at the bottom you divide it by total time. Or the frequency can be 1 over time. If they've given you time and they've not given you number of waves, you just say 1 over the time that you had been given. Not difficult at all. And then we will also look at an example here, a straightforward example that we can also follow is that 6 waves passes a point in 4 seconds. So calculate the frequency of the waves. That is what is required of you. So let's look at this thing. There are 6 waves. So we have total number of waves, and passes at a point in 4 seconds. We have time. Now calculate the frequency of the waves. So we take the total number of waves, which is 4, divide it by the total time. But let's say we didn't have the 6 waves and we just have 4 seconds. We just say 1 over the 4 seconds. Or when we just given the time. Now let's look at period. Period is the time taken for one complete wave pulse, and the SI unit for period is seconds. So formula for period, so here you will be given the period. So the period is the time. That T represent the period. So how to calculate the period is total time over total number of waves. So it's a vice versa of frequency. Frequency is total number of waves divided by total time, and then the period is an opposite of that. Okay, so frequency is equals to number of waves, as you can see here, but time is the opposite of that. Okay, frequency is the number of waves divided by total time. But when we have, so F is this one, but T is the opposite of the F. So when we want T, what was in the bottom for F will be on top, and what was on top for the F will be at the bottom for the T. As you can see here, period and frequency are opposites of each other. And then when we're looking for time, you can see time or period equals to 1 over frequency. And then here is an example that 8 waves passes a point in 4 seconds. Calculate the period of the waves. Here's the solution. So period equals to total time over total number of waves. As you can see, it is the opposite. So it is the opposite. I hope you get that. Now we're going to look at the wave speed. Wave speed is the distance traveled by a point on a wave per unit time. The speed of a wave is measured in meters per second. Now formula for period equals to V, which is the speed in meters per second, and then the speed, which is the V, the wave speed, equals to frequency times wavelength. Okay, so that T, that it looks like a T that is falling down, or the top part is stretched so that it touches the ground. That is the wavelength. So here you are given a example. Calculate the speed of a wave with 10 centimeters. So wave speed should be meters per second. So you need to convert. With the frequency of 150 hertz, now this is the solution. You convert centimeters by dividing them by 100, okay, to get meters. So whenever you want centimeters into meters, you divide them by 100. So there 1 centimeter equals to 10 millimeters, 100 centimeters equals to 1 meter, and 1000 millimeters equals to 1 meter. So there we have calculate the speed of a wave with a 10 centimeter wavelength. So we're looking for speed. Speed is v. Now what is this? The wavelength is 10 centimeter. So when we say 10 divided by 100, we get 0.1. So here if you say this 10 divided by 100, converting centimeters into meters, let's say 10 divided by 100, you are going to get 0.1. Now you will say v equals to 150 multiplied by 0.1, and this will give you 15 meters per second. So that's how it is. Do not be confused with the 10 times 10 to the power of -2. You are still gonna get the very same answer when you do it the way that I have just shown you. Okay, so that is how you do that part. And then relationship between frequency and period, they are opposites of each other. And then here is an example where number 1, you calculate the frequency of a wave that has a period of 0.1 second. So you're asked to calculate the frequency and you're just given the period. So it's 1 over the period will give you the frequency, and then 1 over the frequency will give you the period. Okay, that is easy busy. So here, this right here is makes a complete wave. Okay, and then here and then here as well makes a complete wave. So this is how you get your complete wave, one wave. I hope you can see that what a complete wave looks like. It's very important that you know all these things. So the following diagram represents a wave with a frequency of 10 hertz. That's the direction of the wave. The 30 centimeter is the wave length. Okay, and then now let's look at this. A say calculate the wavelength of the waves. And then the solutions, length of 3 waves is 1.2. So from here to here is number 1. From here to here we have number 2, and then from here to here we have number 3. So we have 3 wavelengths, and the distance of this 3 wavelength, we see it by this. Now this is the distance. This 1.2 meters is the distance of the 3 wavelengths. Okay, so you must keep that in mind when you are asked to calculate the wavelength of the waves. You take that 1.2. And then number B says calculate how long it will take for the 4 waves to move past point C. So how long it will take, whenever we talk about how long is the period, okay, how long it will take to pass point C. So that is how long. There is point C, as you can see it on the graph. If you cannot see it, this is point C. So how long will it take for this wavelength to pass point C, to move past point C? We're calculating period, okay. Now what we are given hertz, so we're given frequency and we want the period. We're not given the time, so we're not given the number of waves and the seconds. So we'll just take 1/10 to get the period. You see, the hertz are on top there. The following diagram represents a wave with a frequency of 10 hertz. So we have that divided, 1 divided by that will give us the period. So it's 0.1 seconds, and 0.1 seconds is for one wave. Therefore, for 4 waves, the period is 0.1 times 4. So this hertz is a wave. One wave is for one wave, okay. So we multiply that one wave by 4. Because of this point C is not a complete wave yet, but you include that half. So let's look at this. Calculate the speed of the wave. When you are asked to calculate the speed of the wave, remember you are looking for V. Speed is V, okay. So that will be the 10 multiplied by the we can still go back a bit, the wavelength. So that T that seems like it's almost at the ground, it's what we call the wavelength. So let's look at this. The wavelength is also the hertz, okay. So we'll get 4 meters per second. So here is an activity. You can just do it by yourself, and I will show you the answer to this. You can pause the video, try to do this, and here are the solutions to this activity. Now we are on Doppler effect for grade 12. And yeah, let's look at that. So here in Doppler effect, what is stationary? It's what is standing still, right? Let's say here we have a listener. There are 3 scenarios, and then here we have an ambulance. This ambulance is moving in this direction. This person is stationary, meaning is standing still, and this ambulance is going to move towards this person, okay. So that's what we say the source will be this car. This is the source of the sound will be this car, and then this person here is the stationary listener, okay. Or they can be an instance whereby the listener is going to pass the car, okay. There are such instances, but let's look at this. Yeah, so let's look at this. The Doppler effect equation. The frequency emitted by the source is constant. Only the frequency detected by the listener observer changes, provided there is a relevant motion between the source or the sound wave and the listener. You can use the following equation to calculate frequency heard by the listener, which is the observer. So FL in this equation stands for frequency of the listener, and then Fs is frequency of the source, which is the one that is exerting noise, and then V is the speed of motion in medium measured in meters per second, and then VL is the speed of the observer, and then Vs is the speed of the source. Okay, if the listener or the source are standing, then the VL will be 0. Okay, the VL, the Vs will be 0. But yeah, here Doppler expression to use after writing the Doppler effect formula using the plus or the minus sign depends on the relative motion of the source and observer. So when the source is moving towards a stationary listener, remember we have a stationary listener, someone standing still at a road, let's say at the side of the road, someone is standing still, the ambulance is passing. So meaning that ambulance is moving towards the stationary listener. A person is standing, it can hear the siren of an ambulance a distance away, but the ambulance is going to pass the standing listener. That's when you use VL equals to V on top over V minus Vs times Fs. Okay, so the first formula, you use it when the source is moving towards a stationary listener. And then the second one, when the source is moving away from a stationary listener. Let's do this. For number 1, here is the listener, and then here is the ambulance. Let's say is the ambulance. The ambulance is moving towards this direction. You are using this first formula. Now, here is the listener on the second formula, and then here is the ambulance. The listener is still standing, okay? Standing still, but the ambulance, when the ambulance has not yet passed the stationary listener, we use this one. Now, when the ambulance has just passed and going away from the stationary listener, we use this one. So here is the stationary listener, the ambulance is going towards this direction, it has passed the stationary listener, we use this one. Okay, so don't forget that, it's very important information that you have to know. And then we have when the listener is moving towards a stationary source. Now, here, the ambulance is just standing there. The ambulance, yes, is making a lot of noise. Oh, and then the listener is, here, the ambulance is now stationary and the listener is moving towards the ambulance. Now, when the listener has moved from the ambulance and is going to this direction, we say the listener is moving away from a stationary source. The source is the one that is making noise, which is the siren from an ambulance. So I hope you guys understand that part is very important that you do. It's a very easy, fairly easy topic. So let's look at an example. Both the source and the listener are stationary. So if both the source and the listener are stationary, you can use the original formula because no one is moving away from whomever. So you use this formula that you are given here. Okay, that's what you use when both the listener and the source are standing still. So they're just next to each other. Now, the siren of a stationary ambulance emits waves at a frequency of 800 Hz. Determine the frequency of the sound heard by the stationary listener if the speed of sound in air is 340 meters per second. So what we are looking for here is the frequency. Determine the frequency of the sound heard by the stationary listener. So we are looking for FL. FL stands for frequency of the listener, and then Fs is frequency of the source, which they say the siren of a stationary ambulance emits waves at a frequency of 800 Hz. So that is the frequency of the source. And then we have the V. If the speed of sounds in air is 300 and F. So no, this is the V is for the speed of sound in M. If it's just V and it's not VL or VS, is the speed of sound in M. Now they are both standing still, so the speed of the listener is 0 and the speed of the source is 0 because they're standing still. Okay, so what happened is that you have V. Let's do this. You have V so you have the V as 3. Let's do this. You have the V, I'll write it here as 340 plus or minus VL 0, and then here you still have 340 plus or minus the VS is 0, and then the FS now the FS is 800, right? We're looking for FL. So you punch all of this into the calculator. So this will be 340 over 340, which is 1 multiplied by 800, and this will give you 800. This whole thing here is 1. Okay, so that is how that calculation was done. So here it says, when the source and the listener are stationary, the frequency observed by the listener is the same as the frequency of the source. So let's here we will say that the source is moving towards a stationary listener. Okay, so we remember that that is the if you remember the formulas that I've shown you, we are using the formula of the source when it's moving towards a stationary listener. So an ambulance is moving towards a stationary listener with a velocity of 30 meters per second. That is the velocity of the source, 30. The frequency emitted by the ambulance is 600 Hz. So that is the frequency by the source. Calculate the frequency that the listener will detect. So we're still looking for the frequency of the listener. If the speed of sound in air is 340, so the V stands for the speed in sounds. And now this has been substituted correctly. It's not as so it is a minus. We use a minus. This has been substituted correctly here. You see, yeah, everything is perfect. I don't have to redo it. So here is when the source is moving towards a stationary listener. So the source here is moving towards a stationary listener. So the frequency observed by the listener is higher than the frequency of the source. Okay, so just know that when the source is moving towards a stationary listener, the frequency observed by the listener is higher than the frequency of the source. Just know that. So the source is moving away. In this example, this has to do with that first one. So here at the second, the other example is that the source is moving away from a stationary listener. So an ambulance is moving away from a stationary listener with a velocity of 25 meters per second. So that is the velocity of the source. The frequency emitted by the ambulance is 450. The frequency by the source is 450 Hertz. Calculate the frequency that the listener will detect. So we're still looking for the frequency of the listener. If the speed of sound in air is 340, yeah, that is how we do it. And it's easy busy. So the V will be the 340, and then the 340 is the V, yeah, plus the 25 multiplied by 450. So that is the frequency of the listener. You see, it's very, very easy. You can try this one, pause the video, and I will show you the answer. So here is the solution to that question that I said you can just pause the video and do, just for practice sake. Another thing that we have to look at in this formula is that when the ambulance is approaching a stationary listener, at the bottom, at the top, we have a plus. You see this, there is a plus or minus. So when the ambulance is approaching a stationary listener, we have a plus on the top and then a minus on the bottom. Okay, but when the ambulance has passed a stationary listener, we have a plus on the bottom, on the top, and a plus on the plus on top and a plus on the bottom. Here, looking at this minus, plus or minus in the formula. So this is when the ambulance is approaching, and this is when it's going, when it is past a stationary listener. It's very important that you know that. Let's look at this example. And the siren of a burglar alarm system has a frequency of 960 hertz. So that is the frequency of the source, which is FS is 960. During a patrol, a security officer traveling in his car hears the siren of the alarm of a house and approaches the house at a constant velocity. A detector in his car registers the frequency of the sound as 1000 hertz. So that is the frequency of the listener. It's always bigger than the frequency of the observer. Okay, when you hear the sound of a siren, it's louder in your ears than it actually is. The speed of sound in air is 240 meters per second. So number A says, so that is the sound in air. And then here says, name the phenomenon that explain the change in observation, that explain the change in the observed frequency. So that is Doppler effect. And then B says, calculate the speed at which the petrol car approaches the house. So that is the speed of the listener. That's what we are looking for. We're looking for the speed of the listener. Use the speed of sound in air as 240 meters per second. So when the listener is moving towards a stationary source, we use this formula here. So with this formula, guys, we have the 340 as the V. This is the formula. And then we have the 340 as the V plus VL all over 340. And then multiplied by 960. And then here we have 1000. So whenever you want to get rid of the denominator, you multiply by 8. Okay, so whenever we are multiplying, just know that we have one term. So whenever you are multiplying, it's one term. But if we were adding, it was going to be a term and a term. So we're going to have two terms. But because we're multiplying or dividing, we have one term. So what we do, we multiply this whole thing by 340 because it's one term. So we multiply by 340. We'll just write it next to the 960, but I don't have space. And then we multiply by 340. So this 340 and this 340 will cancel out each other. That's how it will go here. And then we will have 340 multiplied by 1000. And that will give us 340,000 equals to 340 plus VL, velocity of the listener, and then we have the 960 at this side. Okay, and then the next thing, we want to get rid of this 960, So what we do, we divide by 960 on both sides to get rid of it. We divide by 960 on both sides. So when we say 340 divide by 960, we get 354.16. So let's just take this up. Then this side we are going to get 354.16, and that is equals to 340 plus V1. So I'm not this side, I'm not even going to round off. This is 354,16666 and 7 at the end. So what I'll just do is take this 1,11116 and then move this 3 to the side, because we are adding. We can move this 340, so we'll have 3,54 no, it's 354,16667 plus the 340 will be the VL. Minus, sorry, not plus, we minus, because this 340 was positive this side. When it comes this side, it's negative. So when we do 345,16667 minus 340, we get 14,16. That's right here. That equals to 14,16. So we started here and now we end there. Yeah, let's erase everything. I hope you saw what I did there in order to solve this problem. In fact, it's not 14,16, it's 14,17 when we round it off. Do it on a calculator and you will see how it's done. So that is how this question and this answer was done. So they can be when we're looking for the VL and the VS, it's quite a complicated calculation, so you have to know how to do it. So here is another example. Pause the video to challenge yourself, and then I will show you the solution. So a whistle of a train emits sound waves of frequency of 200 Hz. A stationary listener measures the frequency emitted sound waves at 1880 Hz. The speed of the sound in air is 240 meters per second. Is the train moving away from or towards the stationary listener? That's question number 1. You're going to calculate the speed of the train. And then number 2, will the frequency observed by the passenger sitting in the train be greater, equal to, smaller than 200 Hz? Explain your answer. And then your solution, you have to number ways away from the stationary listener, and then that is number B. Try to do it the way that I have done to see if you understand. And then we have C. That is the answer to number C. So guys, if you are given a graph like this, what you should know is that here at 900, the source is approaching the listener, so the listener is here, and at the 800 the source is going away from the listener. That's what you also have to know when you are given a graph. You should be able to make that an analysis. Okay, just like here. And the solution to that question is here. So I know that it might be a problem for some of you to do this one. So I decided that I should show you how to do it. So for this calculation, we're going to use this formula, right? So for V, we have the 340. Let's write it here. And then at the bottom, we have 340 plus the velocity of the listener. And then we have 2000 equals to 1080. So the first thing that I would do at this point is that I will make this over 1. This is multiplication. And then I'll multiply across. Okay, so I'm going to erase this. When I multiply across, I'm going to do something like this. I'm going to say 1880 equals to 340 over 340 plus Vs multiplied by 2000. I'll just make this 2000 over 1, and then 340 multiplied by 2000 will give me 680,000 over 340 multiplied by, not multiply, plus the velocity of the listener. This will still be 8. And then what do? I cross multiply. And then here, the 340 will multiply with this one. And then this one will be like it's over 1. And then the 680,000 will multiply with the 1. I'm showing you guys how we do it. And then after that multiplication, we will have something like 1880 multiplied by 340 plus Vs equals to 680,000 that we had on top. So we multiply again for 1880 to get rid of it. And then we are left with 340 plus Vs equals to, this divided by this, that will be 361,70. And then when you take the 340 this side and minus it with this side, that's where you get 21,7 SVS. I hope you understand this part. It's very, very important. That's how you do it. So you will be dividing. With physics, you should know your maths quite well. So here we are going to look at the Doppler effect with light. And this is what you have to know, that the universe started as one big mess which exploded to form all the objects in the universe. Therefore, all objects in the universe contain the same type of materials. The atoms in these materials can be identified by the emission spectra, type of light they produce when they are hot. So stars in the universe produce their own light from the hot atoms of their surface. These atoms can be identified by comparing their emission spectra with those of similar elements on Earth. So blue means there's high frequency and red there's lower frequency, okay, with the element on Earth. And then we also have with the element element from a distant star. So blue is high frequency, red is lower frequency. So here's the summary of how a redshift and a blue shift occur. So the redshift occur when the spectrum of a distant star galaxy moving away from the Earth is shifted towards the red end of the spectrum. We use the redshift to conclude that most stars are moving away from the Earth, and therefore the universe is expanding when there is a redshift. So the redshift phenomenon is observed when the light source is moving away from the Earth, and the blue shift occurs when the spectrum of a distant star galaxy moving towards the Earth. So blue shift the stars moving towards the Earth, red shift they are moving away from the Earth. And then here is an example that you can go through, and here are the answers with regards to that. I don't want this video to be long, so this is how you'll be tested on this part of the Doppler effect on light. Thank you guys very much for watching this video. Until the next one.